I'm quite pleased to have Steve Desch here from Arizona State University. Steve got his PhD at the University of Illinois, the Urbana-Champaign campus, after going to the University of Chicago for his master's in astrophysics and Rensselaer Polytechnic for his an MS and BS also in physics. And as I said, we're changing to the next set of potential resource bodies, asteroids. And the resources on asteroids are critically dependent on where they accreted and when they accreted. And when I went to graduate school, it was this nice, consistent and easy story about everything is where it always had been. Everything had accreted in place, nothing had moved around. And what you saw was what you got. And then about 5 years after I learned that, the entire structure just got smashed into 1,000 pieces and reassembled because of planetary migration. And we've started to understand that the evolution of asteroids is critically dependent, as I said, on where and also when they accreted. And so to start out in our looking at the economic resources in asteroids, it's best to start at the beginning. And in the beginning, asteroids were accreting, and they're accreting in some of the strangest places and got moved around. And so Steve is going to tell us about that background. Take it away, Steve. And before you start, I should say the usual rules apply. People around the table can ask questions and make comments verbally. I ask people on remotely to ask their questions and make comments via the chat box, and I will relay the questions to Steve. Go ahead.
Okay. Awesome, thanks. And how long do we have again?
Well, for you, talk for about 55 minutes, and then we'll be taking questions and discussion.
Okay, I might go a little less than that and give more time for questions, because one of the things I'm struggling to understand is exactly what everyone's background is and what you find most interesting. But anyway, yeah, I was charged with the the goal of explaining where and when asteroids formed and how, and of course from a standpoint of resource utilization. So I'm going to go through some of the recently. This is mostly based on this one paper that was sort of a major work that I did with my graduate student at the time, Anusha Kalyan, and who's now a postdoc, and Connell Alexander, who is a staff member at Carnegie Institution in Washington, and he has an encyclopedic knowledge of meteorites, and that was important for this. So, so this is sort of a mishmash of a few things, and I'm trying to advance my slides. Let's see. There we go. So the first thing you should know is meteorites are, of course, the pieces of asteroids that we fall into Earth from asteroids. We have different types of meteorites that presumably have different origins, and these are a few examples of melted asteroids. So these are meteorites that came from pieces of asteroids that had melted. And we have examples of iron meteorites. I think you can see my my cursor, right? You can see that?
Yes, we can.
Awesome. Okay. So iron meteorites are iron and nickel that presumably form from the cores of asteroids when the temperatures got high enough for liquid metal to form, and the liquid metal being denser would settle to the core of an asteroid. And what left behind are examples of just melted rock that's been depleted in metal, and these are called angrites, and these are called stony. I'm sorry, this particular one is an angrite. In general, they're called achondrites. And so this is an achondrite. That just means a rocky melted composition. And then you have examples of what appear to be the in-between. So This has liquid metal that froze into metal, and then you have these olivine crystals that are floating upward through that liquid metal, but the whole situation froze that way. So we have examples of asteroids that clearly melted, and that is presumably due to radioactive elements in them that heated them up. And then we have examples of asteroids that did not melt, and collectively these are called chondrites. And so chondrites are known as that because they have these little millimeter size things in them called chondrules, which I'll try to talk about some more later. But these asteroids did not melt. They're not exactly pristine. They have various amounts of metamorphism, and it could be due to heat of the parent body, and it could be due to water aqueously altering the material. But either way, they are pretty much the stuff that was floating around in the solar nebula came together to form asteroid parent bodies, pieces of which we have today's meteorites. And because of that, these offer a window into what was going on in the solar nebula, which I should explain is the collective term for the protoplanetary disk, or the disk of gas and dust that was orbiting the sun, out of which the planets and all the asteroids and everything formed. Okay, so there are three main types of chondrites that are in our collections, and these are classified as either carbonaceous chondrites, ordinary chondrites, or enstatite chondrites. Enstatite chondrites are very rich in the mineral enstatite, MgSiO3, and they tend to have chemically reduced compositions. And basically we infer that there was not water in the region where those parent bodies formed. At least there was no water ice that was solid that could participate in the growth of the asteroid and be incorporated into the parent body. And probably very little water overall, even in the solar nebula, in the place where these form. And then we have, in contrast, carbonaceous chondrites, and these are also subdivided into a number of different types of carbonaceous chondrites, but I'll get into that later. But basically, these are very water rich in general, and we infer from that they formed farther away from the sun where the temperatures were lower, and therefore could have incorporated water ice as the asteroid was growing. And then you also have ordinary chondrites, which are relatively water poor. They don't have nearly as much water in their structure as carbonaceous chondrites, but they did have some. And so these are inferred to have formed in a place cold enough for water ice to condense, but they just didn't have as much as the region where carbonaceous chondrites formed. So in some sense, we're seeing a progression away from the sun. Enstatite chondrites probably form closer, ordinary chondrites further out, carbonaceous chondrites the furthest out. I should add, these don't have any water like ice in a strict sense today, but what they do have are clays. And so if the parent body had water ice and it was incorporated into its structure, and then it got to some mild temperature, a few hundred degrees Celsius, then the water can react with the silicate rock and form clays. And so that's what these objects have. And so carbonaceous chondrites can have up to kind of 10% by weight water or OH bound in the minerals, in the clay-like minerals. And so that's pretty volatile rich. Ordinary chondrites tend to have something a little less than 1%. Enstatite chondrites would be much less than 0.1 weight percent water. Okay, so that's sort of the main types of asteroids we think are out there, and we are trying to figure out from this how they formed. There's something else you should know. There's a few different types of carbonaceous chondrites, and they're classified on the basis of chemistry, on the basis of oxygen isotope compositions, and a number of other parameters. So we have CM, which are named after the prototype. Miguel is the name of the meteorite that they're named after. There's CV, which are named after Vigorano, CR, CO, etc. There's one special type called CI, which is named after Ivuna. And there's only 5 of these meteorites known that are classified as CI chondrites. But what's really interesting is that they seem to have almost the exact chemical composition as the sun. So this is a plot of the abundance of elements, like the molar abundance of elements in the sun's atmosphere on this scale. And I think it's on a scale where silicon would be 1 on this scale. And so you have things like iron and magnesium are almost as abundant as silicon in the sun's atmosphere. And then on this axis is the same quantity as measured in CI chondrites. So on a scale where the number of silicon atoms is 1, you see iron and magnesium are almost as common. And what's really fascinating is that this 1-to-1 correlation exists for pretty much all of the elements, extending all the way down to some extremely rare ones here. On a log-log plot, it kind of hides some of the uncertainties. These are actually uncertain to at least tens of %, but there seems to be this 1-to-1 correlation. So we can infer that CI chondrites, at least, are forming from the solar nebula somehow, and the solar nebula has the same composition as the sun. There are a few exceptions. You can see that in the carbonaceous chondrites, they have much less carbon and nitrogen than the solar level. So from that, we know that, well, these are likely to form volatile compounds and ices that probably weren't incorporated very efficiently in the asteroids that or whatever that formed the CI chondrites. The rest kind of are represented equally. One other interesting case is lithium, which is much less abundant in the sun than you'd expect from the meteorites. And that's because lithium is actually destroyed by nucleosynthesis in the sun. So, so in some sense, CI chondrites are taken to be what the original composition of the solar system was. I'll kind of address that later. And also for future reference, they do not contain any of what I'll call refractory inclusions, which I'll explain on one of the other slides. Okay, let's take a look at these. And here's a cross section of an ordinary chondrite. And here's a scale bar, 1 millimeter. And what you see is it is indeed full of these little millimeter or less, these are sort of a fraction of a millimeter in size, inclusions, and these are called chondrules. And pretty much everything in this image is a chondrule. And especially some of these, you can see they're round, they have crystal textures, and it's inferred that each one of these was a droplet of liquid rock at some point floating freely through the solar nebula. And then were incorporated into this asteroid that this ordinary chondrite came from. And the droplets, each of these chondrule things, they're called chondrules. Each one is composed of minerals that are kind of standard iron and magnesium silicate minerals like olivine and pyroxene. And you know, they're not too dissimilar from you know, sort of basalt or black sand beaches in some way of Hawaii. But each one of these chondrules, and the word comes from the Greek word for grain. So a grain, you know, like wheat or something is basically called chondrule. So each of these is sort of the size of a seed of grain, and named chondrules. And then the meteorites that have these are called chondrites. And it's very easy to confuse those, but chondrules are found in chondrites, and then melted ones that don't have chondrules because they melted, those are called achondrites. So that's the terminology. But yeah, each one of these was floating freely through the solar nebula and then was melted. And it's an open question, what would melt entire asteroids worth of material, of rock, 1 grain of sand at a time. And then here's an image of an enstatite chondrite in cross section, and it's pretty similar. It's got a bunch of chondrules. Some of them are pretty large. And then, oh, what happened to my carbonaceous chondrite? Okay, I'm missing a slide, but I'll go back to the title slide. This is a carbonaceous chondrite, and it's also full of chondrules, but you're going to see that it's also full of, it has some of these, here's one, white-ish, irregularly shaped, clearly not melted into a liquid droplet. It's just some sort of irregularly shaped thing. It's white because it's rich in minerals that have a lot of calcium and aluminum. And so these are called calcium aluminum rich inclusions, or CAIs for short, calcium rich aluminum rich inclusions. And so carbonaceous chondrites have also a lot of chondrules, and in each of them there's the micron sized dust that kind of cements it together. But the carbonaceous chondrites tend to be enriched and have some abundance of CAIs. Okay, so that's sort of a primer about what meteorites are and the components in them, and something about where we think they're coming from. Now I want to segue to, this was a few slides that I gave reviewing a conference I had been to called the First Billion Years Accretion. And these were some of the results that were presented at that conference. And I think this is relevant to what we're talking about. So first, what is a protoplanetary disk? And we could hardly have imagined what they look like before the 90s, and the Hubble Space Telescope started to take some images of disks in silhouette in the 90s, but these are really the best images we have. These are images, these are false color, of course. These are taken at millimeter wavelengths. So sort of, very long wavelength radiation. And this is using the Atacama Large Millimeter Array, which is a whole bunch of millimeter wave telescopes that are linked together in Chile. And that gives them the ability to map out the structure of these disks at fine spatial scales. So there really need to be scale bars on these, but this disk, TW Hydra, this gap here, this is kind of like tens of AU. And AU is the distance between the sun and the earth. So this is sort of solar system size. This one we happen to be seeing almost face on. It's a disk, but we're seeing it face on, and it's really amazing. You see more emission from the regions near the star, and you see these gaps that exist at certain radii, and we're trying to figure out what that's due to, but it could be due to planets already having formed in this and clearing out gaps. Here's another one. This is HL Tau, HL Tauri. And this is seen not quite face on, a little bit more edge on. And again, this is sort of solar system size, 70 AU or something like that. And you're seeing gaps in the disk as well. So it's absolutely amazing. And it's a little bit surprising to astronomers because these disks are pretty young. This disk, for example, is only 100,000 years old. We know that protoplanetary disks tend to last for, 3 million years, 5 million years, something in that time frame. And to have these gaps in the disk at an age of only 100,000 years means that it suggests strongly that planets started forming really quickly in the lifetime of a protoplanetary disk. So that's going to have to be in the back of our minds as we try to figure out what was going on in our own protoplanetary disk 4.5 billion years ago. Here's another very interesting thing that was presented at this conference. This conference took place 2.5 years ago. This is telling us something about asteroids and how they formed. What this group did, Delbo and Walsh, is they identified collisional families in the asteroid belt. So right now, the asteroid belt that exists between Mars and Jupiter, between about 2 and 3 AU, That region is full of tens of thousands or hundreds of thousands, depending on what size cutoff you want to use, asteroids. And most of these are just pieces of larger asteroids. And we know this because we can see maybe there's one large asteroid, and then you see a lot of other smaller asteroids that have the same orbital elements. They have the same distance from the sun, eccentricity of the orbit, inclination of the orbit. And so they must have been pieces of that larger one. And so you can identify whole families of asteroids that orbit the sun in the same way, and that obviously derive from collisions that produce fragments of this larger one. And so those are collisional families. A famous one is from the asteroid Flora. Flora is a pretty large asteroid. It was the 8th one discovered, and it orbits at 2.2 AU. And so on this graph, you're seeing different asteroids plotted based on how far they orbit from the sun, in this case 2.2 astronomical units, and 1 over their size on this axis. So Flora is pretty large, so it is at the bottom here. And then what you're seeing are other things that are orbiting at the same distance as Flora, but are obviously smaller, so they're higher up on the scale. And what happens when you have a small chunk of an asteroid that comes off of the big asteroid, the small chunk being smaller is more subject to other forces other than gravity. One of the most important things is the Yarkovsky effect, which is a way that asteroids absorb heat, sunlight from the radiation from the sun, and then they re-emit it. And the way they do that allows them to change their distance from the sun. And it could go further away or closer to the sun. It's kind of random. So this collisional family, you'll see, is distributed in a way that the smaller you are, the more you are up here, the more time, the more distance from the original orbit it could have progressed. So you could have had pieces spiral in towards the sun or away from the sun. And so they should fall in this V shape. And so pretty much all of these objects are members of the Flora collisional family. And you also have other collisional families, the Polana and other ones. So that was really interesting to see that such a large fraction of asteroids are parts of these collisional families. But interestingly enough, you have a few. These are at certain distances from the sun, and they're pretty large. These could not have been part of any collisional family. These must have been actually the size of asteroids just start with. So, so this technique of finding all the collisional families is allowing us to figure out the original sizes of asteroids, and that's a big clue for how they formed. And there's a growing understanding that, in fact, asteroids are born big, and they all started with a particular size, which is a diameter of around 100 kilometers. And any asteroids that are much smaller than that are simply chunks of asteroids that had formed that size. So this is another way of saying that what they did is they only got the primordial asteroids that did not appear to be part of any collisional family. And then as a function of their diameter, you can plot how many of those primordial asteroids they are. And they tend to follow this distribution here. And so there's not that many that are smaller than about 30 kilometers. And the numbers get smaller as you get to larger ones. And then you have some very large ones that may have, I don't know, they're just extra large, or they may have formed from a merger of a few, but not very many, Vesta being the largest one.
Steve, what's the physics that's driving this 100-kilometer diameter kink?
Yeah, so what seems to be happening is that there's a process in the disk that is creating a distribution of sizes in this size range, like 30 to 100 kilometers. And then it may be possible that if you have a population of 100-kilometer sized bodies, they could find each other and merge, and that's going to be a pretty improbable process. So the numbers that are much larger may go down. That could be why there is this kink in here. But what this is telling us is that there is something that creates a large, a population of very large bodies, and it does so very quickly. And I hope to get back to that towards the end, but it seems to be this model called streaming instability. That is a way for particles to find each other very quickly in the disk. When the conditions are right, in a few orbits, you will have just formed an asteroid.
Okay, very cool.
Yeah, so the size distribution is giving us a lot of clues into that process. And yeah, I won't go through this, but it seems to successfully or pretty well match models of this thing called streaming stability. I won't explain the graph, but I'll say what streaming instability is. As particles go around the sun, they tend to orbit a little bit faster than the gas. I'll explain why in a few slides. And the gas tends to exert a drag on them. So yeah, you have particles that are trying to orbit the sun, but they're trying to orbit through the protoplanetary disk gas, and that slows them down. But if there's particles behind them orbiting in sort of the same radius, they're not slowed down so much because they're like drafting on those first bunch of particles, sometimes called the Peloton effect, like the Tour de France bike riders. So once you get some sort of clump of particles that can shield the particles behind them from the drag force, those particles can catch up. And so you have this sort of logjam effect, and you just have a very large concentration of particles. It tends to feed on itself. Once you have a larger collection of particles, they can shield the ones behind them even better. And so it just allows a lot of particles to catch up all at once. And so within a few orbits around the sun, you can create a logjam, a pileup of particles that are massive enough to make 100 kilometers size asteroid. And this is numerical simulations of that process and the size distribution you get. And it seems to match okay so far. All right. And the streaming instability itself, these sorts of numerical simulations tell us something about the size that you need. And it would be very convenient if the size of particle you'd need is the size of chondrules, because the asteroids and the meteorites, they're just full of these chondrules. Those are millimeter-sized particles. Unfortunately, it seems like the numerical simulations tell us that the particle size you need is something closer to 10 centimeters. So that's a lot bigger than the sort of millimeter size particles that we're talking about. However, it actually does seem likely that you have a two-stage process. What happens first is that chondrules somehow are concentrated into big aggregates of 10 centimeters. And then the 10 centimeter size aggregates are what streaming instability and numerical simulations allow to bunch up and form asteroids very quickly. So there was some evidence also presented at this conference that in this one particular meteorite, for example, you have chondrules here, they look pretty similar, but they were able to identify based on the colors that you actually had two lithologies. And in the light lithology, the chondrules have the same size, but they are clearly chemically related to each other in a way that the ones down in this dark lithology are not. And so these authors inferred that the meteorite and the asteroid this meteorite came from actually incorporated 10 centimeter size aggregates of chondrules. And the chondrules were probably concentrated by turbulence into these aggregates, and then those aggregates were lumped together by this streaming instability very quickly into asteroid-sized things. So I'm pretty convinced that this is the way asteroids form. That first you have millimeter-sized chondrule things that are just floating through the solar nebula. Turbulence sort of groups them together into sort of beach ball size, fluffy dust bunnies of chondrules that are somehow sticking to each other. And then these things are what can bunch up by this streaming instability peloton effect, and they will, when the conditions are right for that, it will very quickly form a 100-kilometer size asteroid, something in the 30 to 100-kilometer size range. And then, yeah, basically that's how asteroids form. And what I'll get to next is where and when did they form, but that's I think a major step in our understanding of asteroids. And so I'll pause there if you have any questions.
Yeah, so I do research on the organics in the matrix. Where do you think the matrix and asteroids came from?
So the matrix refers collectively to everything that isn't the chondrules or the CAIs. And so I guess we could include micron-sized silicate dust, and but of course there is also organic material, and then water is circulating through that matrix and altering the material. So it's a mess. There certainly was, though, just micron-sized dust that was in the solar nebula, and you could have had, you know, micron-sized organic material as well, or it could have been a coating on some of that micron-sized silicate dust. Either way, it was floating around. It probably rimmed chondrules, and that's got to have been part of the picture, that chondrules have this micron-sized dust sticking to its outside, and then that maybe help them collect together. But you know, beyond that, I don't know. I don't have much to say about the matrix.
Do you have a few words to say about ices?
Yeah, so the ices must have been present as well. These probably were coating micron-sized grains, possibly as well chondrules, because in any of these environments where the temperatures were low enough, water vapor would have condensed as ice. It probably would have condensed onto the particles that have the largest surface area, and the particles with the largest surface area per mass are the micron-sized dust particles as well. So the matrix probably incorporated a lot of ice as well. Once it's on the parent body, it probably melted, and the liquid circulated and went somewhere else on the parent body, leaving behind an aqueously altered matrix, and maybe altered some of the chondrules. And that probably just happened on carbonaceous and ordinary chondrites, and probably not at all on enstantite chondrites.
About how much do electric fields affect this formation?
So it's funny because large-scale electric fields might have existed in the solar nebula, and I did some of my original work on trying to assess whether lightning could have been triggered in the solar nebula, and I would say maybe you could do that, but I doubt it. But it sounds more like you're talking about the coagulation process, and how charge on the particles affect how they lump together. And we know for the very smallest stages, as you're going up from micron size up to millimeter size, things like van der Waals forces, possibly particle charging, did play an important role in helping them lump together. We're not really sure, but what we know is that that's not a difficult stage for particles to find each other and lump together. It's very easy. Lots of models predict from a lot of different mechanisms that they should coagulate from micron size up to sort of centimeter size. Beyond that, it gets really difficult to explain how particles group together. And it's been a mystery for a long time. And I think what we're finally understanding from this sort of work is that they don't really lump together once they reach centimeter size. Well, they get up to the beach ball aggregate size, but beyond that, you don't make meter size things that lump together into 10-meter size things that lump to 100-meter size things. It just leapfrogs directly from this stage where it's easy for stuff to lump together to 100-kilometer size. All right, so I'll move on to some slides. I'm going to skip that one. Okay, so here is an image of a carbonaceous chondrite, and this is the one I was hoping to show you earlier. Here's a large CAI, and these are very interesting inclusion in meteorites, and for one thing, they are the first solids to form in the solar system, And you know, there are pre-solar grains, but these are the first things that minerals that formed in the solar system. They had radioactive elements like aluminum-26. That is an isotope that decays with a half-life of 700,000 years. And no other objects in the solar system had more aluminum-26 than they did. So we infer that they formed first of all the things. And so and they all formed very close in time with each other, actually. We measured and they form from very refractory minerals. These are minerals that condense at temperatures above 1400 Kelvin, very high. They're abundant in carbonaceous chondrites. When you open up and polish and make a thin section of a carbonaceous chondrite, like this one of Allende, they tend to look like this. You're very likely to find a CAI in them. They exist in ordinary and enstatite chondrites, but they're pretty rare. So whereas they are about 3 chondrites, and there's basically none in CI chondrites. So I kind of don't want to go through this, but we can calculate what minerals form at different pressures and temperatures in the solar nebula. This is from Abel's work in 2006. And CAIs are formed of these minerals that you see here that indicate they formed at temperatures, 14, 1600 Kelvin at pressures of something like 10 to the minus 4 bar. So very close to the sun sort of conditions. You only reach those temperatures very close to the sun, and those pressures are also indicative of the disk when you're close to the sun. And by this we mean much less than 1 AU from the sun, maybe a few tenths of an AU. Okay, so this is a table from our paper showing the different types of chondrites. Enstatite, there's 2 types of enstatite chondrites. There's a rare other chondrite called R chondrites. You have ordinary chondrites, which are classified as HL and LL. These, by the way, refer to the amount of iron metal that exists in those chondrites. So these have high, low, and very low amounts of metal in them. Enstatite chondrites have a lot of metal. Carbonaceous chondrites have less, although CR have a lot. I don't know. Anyway, these are 6 types of carbonaceous chondrites. And it's been tabulated in the literature. What is the volume percent of CAIs in these different meteorites? These are from 2 compilations, and here's the numbers we adopt. And this column gives you the abundance of these refractory elements: calcium, aluminum, titanium. These are the elements that will go into minerals at high temperature. And this is their abundance relative to magnesium, scaled to the same ratio in CI chondrites. And so you can see that these carbonaceous chondrites are enriched in refractory elements: calcium, aluminum, titanium, etc. And the other ones are depleted in them. And that's a little unusual or counterintuitive, because these are the ones that form close to the sun, and these form far from the sun. And so somehow these ended up with more refractory elements. They also have more CAIs. And the amounts of refractory elements are high in part because they have CAIs that have a lot of those elements, but that is not the whole story. That doesn't fully explain that trend. And then here's another table from our paper, and there's a lot of information in here. But basically, we're trying to figure out when these different asteroid parent bodies came together, formed. So in these columns, we have, for all these different types of chondrites, and now some achondrites as well, we have the time we think the meteorite came together, or I'm sorry, the meteorite parent body, the asteroid, came together based on how hot they got. So we know that these different chondrites got hot. Some of them got hot enough to melt because they had radioactive elements, including and especially this aluminum-26. And so if you form late, there's less aluminum-26 left to heat up the body. And if you form early, there was more of it and it got hotter. So based on thermal models, you can estimate when the asteroid came together so it would have enough aluminum-26. We can also use radiometric dating, aluminum, magnesium, hafnium, tungsten. There's a whole bunch of isotope systems that we can use to date when chondrules within these chondrites formed. And we can also date post-accretionary events, like if water flowed, form carbonate minerals, we can use manganese chromium dating to figure out when that happened. So presumably those things occurred after the parent body formed. Chondrules had to form before the parent body formed. These are the dates of the parent body formation. And they're pretty consistent. The uncertainties in this data are pretty high. But there's a pretty consistent story. Ordinary chondrites seem to have formed between 2.2 million years after CAIs. Carbonaceous chondrites form in the sort of 2.5 to 4 million year time frame. Ancestor chondrites form a little earlier. That's actually just based on thermal modeling almost entirely. And then achondrites, like these guys, they melted. And so they must have formed earlier. We don't have dates on the things that made up these bodies because they melted, but we have the thermal models and we have some post-accretionary events as well. So these tend to form like 1 million years up to maybe kind of almost 2 million years.
Steve, question. CAI or CI carbonaceous chondrites have the most water and the least CAIs. Is there a relationship between the two?
It's a little tricky. I'm going to say they formed further away from the sun than any other meteorite. So in a sense, that is the story why they have a lot of water and a few CAIs. But it isn't quite that simple. There's this time element as well. You need to form a meteorite that's actually going to survive passage through the atmosphere and land on Earth that we can collect. You have to lithify it, and so you have to actually melt the water ice and have it react with the matrix and form minerals and bind it together. So there is that timing event. So if you form further away from the sun, you could have more ice, and then you're a comet. And you would not survive passage through our atmosphere. And if you form closer to the sun, you could have less ice and more CAIs. There's some trickiness in how you actually turn these into meteorites.
Okay, thanks.
Excuse
Sure.
me. I have
Yes.
a question. So if older chondrites have more aluminum-26 in them, wouldn't they wouldn't they appear more processed today because they had more thermal heating?
Yeah, so the earlier you form, the more processed you are, generally speaking. So these chondrites, these formed very early. And so at the time they formed, more of the aluminum-26 was live and they got hotter in the end. And then these guys were less processed and they didn't melt the chondrules. And did that answer your question?
Yeah, sorry, I was a little confused there. So the CI chondrites formed later than everything else, but they're the least processed, so they appear older. Is that right?
Oh, yeah, well, okay. So CI chondrites, they're often called pristine. And, generally speaking, the later you form, the less aluminum-26 heating you experience and the more, pristine you can keep those objects. There has been, for decades, this sort of baggage in the community, this bias that says if something is pristine, it must have formed first. But it's really backwards. It's if you want to be pristine, you have to have had nothing happen to you. In a sense, that means that you formed late.
Awesome, thank you. That cleared up a lot.
You're welcome. Yeah. Okay. So why are these CAIs in carbonaceous chondrites when they formed 2 to 4 million years after CAIs themselves formed? And this is a longstanding problem called the CAI storage problem. And this gets into some of what I was talking about earlier. Gas orbits the sun a little bit slower than particles. So if you imagine a particle like a CAI, it's kind of behaving like a planet. It feels a gravitational force towards the sun, and you could say that balances the centrifugal force or acceleration away from the sun. And if you equate those two, you find that it should orbit, if it were at 1 AU, it would orbit at 30 kilometers a second. Gas, also a blob of gas, orbits the sun. It feels a gravitational acceleration towards the sun that balances the centrifugal force. But also gas can feel a pressure force. And there's a tendency for the pressures to be higher, closer to the sun than further away from the sun. And so there's going to be an outward pressure gradient force. And that's going to reduce the speed you need to balance the centrifugal force against the gravitational and pressure force. So gas will tend to orbit a little bit more slowly, and at 1 AU it'll orbit at 29.97 kilometers a second. So it's about 1 part in 1,000 less, 30 meters a second. But this is why we say these particles have a tendency to orbit a little bit faster, and so they're constantly trying to orbit the sun through all this gas, or from the frame of reference of the particles, they feel this headwind. And that headwind exerts a drag force on the particles that causes them to lose angular momentum and spiral into the sun. And CAIs are of a size that they should spiral into the sun in a few 100,000 years, less than 1 million years. If a particle is very small, then it's going to just be swept up with the gas. And it will try to spiral into the sun, but it'll end up just orbiting with the gas. And so maybe the gas will spiral in, but slowly. So small particles tend to stay in the disk, but large particles feel this drag force, and they tend to spiral in towards the sun. So this has been known for 40 plus years, that things the size of CAIs just should not exist in the disk for 4 million years. And so theories have been made up to explain why this is, including there must have been asteroid made out of CAIs, and then it broke apart and they got back into the disk or something like that. But that doesn't actually work. But there's a related mystery here. If CAIs are in the disk and they form near the sun and they want to spiral into the sun, why are they most common in carbonaceous chondrites and not at all, I mean, they exist, but they're rare in ordinary anisotite chondrites? And then why again are they absent in CI chondrites, even though those are carbonaceous chondrites? So big mysteries. And why, related question, why are carbonaceous chondrites enriched in refractory lithophile elements, where refractory elements go into minerals at temperatures indicative of the fact they form near the sun, and just where do they all form? And so that was one of the questions I was trying to answer. And thanks to those ALMA images, and thanks to some new understanding of disk processes, we now understand that our own solar system probably had these gaps in the disk as well. And that changes a lot. And it's believed that the formation of Jupiter probably opened up a gap in the disk. So as you look at the pressure in the disk as a function of radius, you have more material near the sun, and then it tends to fall off as a power law. Imagine this is a log-log plot. It tends to fall off. And any region where you have pressure dropping off with distance from the sun is one where there is an outward pressure gradient force. Gas moves more slowly than the particles. Particles feel a headwind. Particles spiral into the sun. So in this region here, in this region here, the particles are going to spiral into the sun. And CAIs will spiral on 1 million year timescales. If you have Jupiter form and it opens a gap in the disk because it's sucking up the gas in its vicinity, it's accreting it, and also kind of causing it to move away from it at the same time, you're going to have a region of low pressure around the planet. And in this region, the pressure drops off very quickly and particles spiral in. But in this region here, the pressure actually increases with radius. And so the gas will feel an inward pressure gradient force, and it'll orbit the sun faster than the particles, and the particles feel a tailwind, and the particles will actually spiral out. So it's been known, again, since the 70s, that if you have a situation like this, particles will collect in the region where the pressure is maximum. And that'll exist somewhere right outside where the planet is opening a gap. So yeah, in a nutshell, if this is where carbonaceous chondrites form, this would be a way for them to form farther from the sun, and yet be in a region that has a lot of CAIs. And the CAIs want to spiral into the sun, but in this region, they don't spiral into the sun, they spiral into this pressure maximum, and they can be trapped there for millions of years. In this region, the particles just spiral into the sun. And if this is where astatite and ordinary chondrites form, this would be a region where you're pretty much depleted in CAI. So even though this is closer to the sun, and this is closer to where the CAIs originally formed, this is not where they're going to be most abundant after a few million years. So in a nutshell, this is the point of our 2018 paper, and we use this to explain and resolve the CAI storage problem. But then we also go on to model the disk. So yeah, I showed you an image of this disk. There's a lot of reasons why we think that our protoplanetary disk had a gap in it. The most important one is this paper by Croyer et al. 2017, very recent paper that looks at the isotope ratios in materials that we think formed in like the inner and outer parts of the solar system. And these are very distinct, and they can put a time on it. And so they invoke the existence of a Jupiter at an early time, in like 500,000 years to 1 million years in the formation of the disk. Let me get back to that idea. So I'm gonna, for the sake of time, not describe the model very well. I made a model, and we predicted if you had a gap in the disk, this is how much material there is per area. We predicted where surface density should be, what the temperatures are in the disk, and then how much CAIs there should be. And so this is as a function of the distance from the sun. This is what percentage of the solid's mass there is CAIs. And these are different times. This is at 500,000 years. And at 500,000 years, there's a lot of CAIs closer to the sun. And they kind of spread out at first and end up going a little bit further away, but not that much, because the sun inside 1 AU, and then they kind of diffuse out, but then they spiral in. And at 0.6 million years in this model, we put Jupiter, or the core of Jupiter, at 3 AU, and I'll have to explain why that is, but it was the only way to make the model work. And after it forms and it opens this gap in the disk, the particles inside 3 AU spiral into the sun and are lost, and outside the sun, they get trapped in that pressure maximum, and so they're concentrated there. And we can do the same with refractory elements. And this graph compiles all the information into a single graph. So this is as a function of distance from the sun and time after CAI formation. This is what I think was going on in the disk. And so I think Jupiter probably formed right around here at 4.5 AU at 500,000 years. And it probably migrated into this location, and then it stalled and it started to accrete gas, and it opened up this gap. Inside of it is where the ordinary and astatite chondrites formed. Outside of it is where the carbonaceous chondrites formed. And what's really interesting to me is we can plot this blue region is beyond this line is where it's cold enough for water ice to condense. And those meteorites, those asteroids can accrete water ice. So carbonaceous chondrites formed in a region that probably had a lot of water and probably it was cold enough for them to accrete water. And these guys accreted a lot of water. Ordinary chondrites formed in a region that was cold enough to condense water ice, but notice that Jupiter forms while it's still pretty hot throughout this whole region, and this region is hot. It's cold enough to have water ice here, but it doesn't mean that it has as much water ice. That water ice would have to get from here to here, And the water ice, if it's on particles that are trapped in this pressure maximum, you could also keep the ice from going into this region. So this is probably why these guys had some water ice, but not as much as carbonaceous chondrites. And then the astatite chondrites formed in a region that was depleted in water. Any water vapor in this region probably diffused over here and froze. So these were very dry. And many of these different bodies, I mean, these seem coincident with the locations where we think the chondrites formed. So H chondrites have been associated because of the similar reflectance spectra to the asteroid 6 Hebe. LL chondrites have been associated with A flora, and the regions where we think that you can match the models and basically explain the amount of CAIs in them and the refractory element abundances, we have a nice match, but they have to form at these locations where we think that some of these other asteroids are known to have formed. Let me just say what I mean about this. What we did is for each of the different chondrites, we have the data. We have the data on how much CAIs they had and how much refractory elements they have and when they formed and some vague idea of where they formed. And then what we do is we have this model and it calculates based on, well, we're just looking for any region, time and place where we can try and match the time, the refractory element abundance, the CAI abundance. And it turns out we can find times and places that do that and explain basically 16 different types of meteorite with one model. And there's very few exceptions where things aren't exactly, but it's a pretty good match overall. I can keep going for a little while longer, but how am I doing on time?
Well, we can handle a little bit longer. I had a question about CIs. Do you want to expound on those guys?
Yeah, so the CI chondrites, effectively, they have to form very far away so that they have basically no CAIs. The CAIs diffuse out to beyond 3 AU, and then you know, they get trapped in this region. The CI chondrites have to form much further away so that they don't have any of those CI chondrites. They also have to form pretty early. It's more restrictive than that, though, and I don't think this was appreciated before. I didn't appreciate it before I wrote this paper. This whole region is depleted in refractory elements. The inner disk is depleted because you were able to form CAIs here. And a lot of the CAIs spiraled into the sun and are just lost. And they took these refractory elements with them. And this region is enriched in them. CI chondrites are a good match to the sun in terms of refractory elements. They're pretty close. And that's hard to explain when you realize that this entire region, it has been depleted in refractory elements. And that really, more than anything else, constrains the CI chondrites to have formed very far away from the inner disk, or else they would have mixed, the material they formed from would have mixed with the inner disk and been depleted in refractory elements. So they probably formed kind of out beyond Saturn, actually, and are more similar to comets than the other meteorites.
And also the other piece of evidence would be that they don't really have any chondrules either.
Right. They may have had chondrules and have been aqueously altered to death, but that is debated. They probably formed by a similar process, though, but they don't have any CAIs, and that's pretty restrictive.
Okay.
Yeah. So let me mention the chondrules thing. So one of the things that our model does, I got to say, we were criticized because we have this model, we match all of these things. And everybody says, well, you fine-tuned the model. And they're like, yes, we did. We had about, I don't know, 5 to 10 different parameters we can play with, and we had to fit dozens of pieces of data. And I think that the fact that we could do that with one model is a success, but nevertheless, it was viewed as fine-tuned. So the referee of the paper suggested we use it to predict something that hadn't been done before. And so, you know, that wasn't part of the original model. So what we have as a result of the model is saying, we can say, well, these different chondrites, they formed at these locations at these times. Well, we have a model for the disk, so we can say how much material there was in the disk, what its density was, what its temperature was, et cetera, what the level of turbulence was. And we can use that to figure out what size of particle should be concentrated by turbulence. So I mentioned how we think that these meteorites are forming from aggregates of chondrules. The chondrules were aggregated together into these beach ball sized things by a turbulent process. And the theory of that in these papers by Jeff Cuzzy says if you know the density of the gas and you know the level of turbulence, you know the temperature, you should be able to predict the diameter of the chondrules that are concentrated by turbulence. And so we can calculate this for each of the chondrites that we have. So on this, this is a graph I sort of made. This is the diameter of the chondrules that we predict should be concentrated by turbulence at the environment where all of these are forming. And this is the actual diameter of the things in those chondrites. And if the model is successful, these should fall in this one-to-one line here. And I want to point out this formula has things like the surface density, the level of turbulence. These are uncertain by orders of magnitude. So we could have been factors of 10 or even 100 off. In fact, for over half of them, we are dead on with this model. And there are chondrule-like things concentrated in CI chondrites, and because they form further out and the conditions are different, they should be smaller, and they are. Some of these are off by a factor of basically 2, but I think that's pretty successful for a model where these could have been off by orders of magnitude, and again, half of them are right on. So we have a pretty predictive model for what size of things should come together to form the chondrites by this turbulent concentration followed by streaming instability, which is scooping up these aggregates in a few orbits to make asteroids. I think that's pretty much, that covers what I want to say, although I've got some concluding slides, but I'd rather just stop there and ask if you guys have any questions.
Okay. Questions?
If the carbonaceous chondrite formed outside of Jupiter, then how did they get to where they are now?
Oh, great idea. Yeah, great question. So going back to this slide, this is how I infer the evolution of the protoplanetary disk plant. I actually think probably what happened was there's a lot of reasons why the biggest planet should form near the snow line, this region where the boundary between where ice can exist and can't. It probably formed a 20 to 30 Earth mass core here and reached this region at 3 AU. And then at that point, it started to get big enough to open a gap, and then its migration slowed down. And so the solar system was split in two while all these asteroids were forming. The inner disk, you know, these things formed here. And then probably, you'll notice this good correlation between where the model says, you know, the Vesta meteorites have to come from and where Vesta is, and where the LL chondrites come from and H Flora is, and H chondrites is Hebe. So I think that this region probably did not suffer a lot of migration afterwards. The asteroids that formed here probably stayed here. Yeah, but then Jupiter stayed here 3 AU. Eventually it has to get to 5 AU. That's where it orbits today. And so sometime after 4 million years, because we do have these guys forming in place and successfully explained by the model, probably after 4 million years, these objects, Jupiter probably started to migrate outward. There is a model called the Grand Tack model that actually postulated that Jupiter formed out here, migrated all the way in 1.5 million AU, and then Saturn formed, migrated in faster. The two got into resonance. They both moved outward. I don't like some aspects of that model. I think Jupiter stopped at 3 AU and stayed there. But I'm happy enough with the idea that Saturn forms, catches up with Jupiter, and then drags it out through some dynamical magic. When Jupiter migrates out from 3 to 5 AU, it's going to go through this region and it's going to scatter the carbonaceous chondrite parent bodies over a wide range. And that is probably how they ended up in this region here between sort of 2.5 and 3 AU. And I should add, these meteorites are associated with, spectrally, with S-type asteroids, which orbit sort of 2.5 AU. These guys are associated with C-type asteroids, which orbit sort of in a broad range from 2.5 to 3 AU. And that probably happened. And then there's a lot of other things you can learn from this graph. Like there's nothing in the inner disk that formed after 2.2 million years. Probably our inner solar system was depleted in gas after that point, and nothing could form after that. And that would make our sun and our protoplanetaries very much like what are called transition disks, which are known to exist around other stars. The inner parts of disks tend to disappear at 3 million years, and then later the outer parts disappear. So yeah, I think Jupiter scattered these guys into this region while it was migrating outward.
Steve, would you expect a smooth transition from CI-like material to comets and a lot of kind of intermediate objects?
Yeah, I think so. Probably, and I'm just speculating here, but I'm imagining that the CI chondrites formed in the pressure bump beyond Saturn. But it's hard to say. But yeah, given that the CI chondrites probably had a lot of ice, and it happened to melt, that let them lithify. But if you formed CI chondrite-like parent bodies in the same region, but at a later time, they simply might not have enough aluminum-26 to melt and have water flow through them and lithify, and that would literally be a comet at that point. So it's sort of just the amount of ice and how much it was able to melt, and that comes down to when it formed, that determines the difference between CI chondrites and comets.
So do you think that lithification process is a key definition of the difference between a comet and an asteroid?
It very well could be, yeah. I mean, just to have a meteorite that we say tracks an asteroid, you have to have a relatively low amount of water ice in it. We do have examples of interplanetary dust particles which are not too dissimilar from carbonaceous chondrite material. We think they're coming from asteroids that are in this region, 3 to 4 AU, and these are spectrally associated with D-type asteroids. There is a consensus that D-type asteroids that orbit sort of at 4 AU, they simply weren't able to reach temperatures that allowed them to lithify, and so these are sort of comet-y sort of asteroids. And in general, the distinction between asteroids and comets is not a sharp boundary.
Right.
From the chat box, is there a relationship between carbonaceous asteroid types and albedo?
Dark.
Well, carbonaceous chondrite they're believed to come from C-type asteroids, which are quite dark. I'm trying to remember the albedos.
Well, that's kind of down my line, and I would say that the more refractory carbonaceous chondrites, like the COs and the CVs and the CKs, are kind of bright. And universally, the more water rich you get, the darker you get. And so CIs and CMs are very dark, and CRs are kind of intermediate.
Okay.
I like the idea of the Jupiter or the Saturn pressure bump maybe making the CIs. That's something that interests me a lot. Do you have to be Saturn size to have a decent enough pressure bump to make a class of things, or can Uranus and Neptune have their own little class of semi-asteroids?
It's a great question. The theory behind what it takes to open up a gap, or not necessarily deplete a lot of gas, but at least to provide a pressure maximum beyond it, there is a minimum size you need, and it has to do with, I think it scales as h/r cubed. So as you go further out in the disk, it kind of, from that aspect, gets harder. You need to be more massive, but I think there's other factors as well. So you kind of need to be sort of 20 to 30 Earth masses, and we think Jupiter's core was that massive. And of course, as you accrete gas, it could do it. Uranus and Neptune might not have been able to open a gap and collect material in the same way, but I think Jupiter did and Saturn would have.
One other thought, you know, the surface density of material drops off pretty rapidly once you get past where Jupiter and Saturn are accreting. So your thought on comets is that not only are they accreting more volatiles, but and the CAIs have already been depleted, but that it just takes longer to accrete them?
Yeah, the surface density goes down, so it takes longer to accrete. You have some of the same processes going on, though. And so in the, we haven't even talked about the whole Niesmall and everything, but we think that after the protoplanetary disk went away, Jupiter, Saturn, Neptune, then Uranus were probably situated between 5 and 15 AU, and then there was a disk of material that would later be scattered to form the Kuiper belt between 15 and 30 AU. And in that region, you would have formed a lot of Pluto-sized things. And we think that that region was much more massive than it is today, probably at least 100 to 1,000 times more massive than the current Kuiper belt. And it would have had thousands of Pluto-sized things in it. And so these had to form by some process, and we think that it was probably this streaming instability process, but it somehow works better the further out you go, and makes larger objects. So the same process that's making asteroid-sized things in the asteroid belt is making Pluto-sized things in this primordial Kuiper belt, but it does take longer. And so those objects probably did not start forming until 4 or 5 million years. And we have I've worked on geophysical models of these objects that suggest that they couldn't have had that much aluminum-26. They must have formed at around 5 million years after CAIs. And I'll point out that Ceres is itself probably one of these Kuiper belt objects, and it probably formed in the vicinity of Saturn and was scattered into the asteroid belt along with some of these carbonaceous chondrite parent bodies during some stage of planetary migration. Yeah, this Ceres is very unlike all the other asteroids. Vesta looks like a big asteroid, but it seems to be made of rocky material that formed in the same way other asteroids did. It's sort of the largest size you'd expect for something formed in the asteroid belt. Ceres is the size and density and composition of a Kuiper belt object, and so it's been speculated for some time it probably formed in the outer solar system and was scattered inward.
You're destroying my cherished illusions. How do you circularize something as big as Ceres?
Right. Yeah, so what you need to do is, if it's scattered, presumably it's first put onto an elliptical orbit, and then, yeah, you've got to end up getting it on a circular orbit. That's hard to do once the gas is gone, and we think the gas was probably gone in the asteroid belt region after 2.5 million years, and if Ceres didn't even form until 5 million years, you can't rely on that. But there's the opportunity to circularize by dynamical friction. So if the asteroid belt was a lot more massive than it is today, and we have a lot of reasons for thinking that too, we think that it was depleted at a later stage of Jupiter migration, then to me, it seems possible to inject Ceres and frankly a few others, Pallas, Hygiea, who knows what, into the asteroid belt, circularize them by dynamical friction with a larger population of asteroids, and then that asteroid population is depleted.
Okay, very interesting. More stuff, more questions?
Hi, is there any way to determine basically where a parent body would have formed based off of, say, how much material we found on Earth?
Oh, how pieces of asteroids get to Earth is a complicated story. And it has a lot more to do with how close those asteroids are to a resonance than anything else. So the asteroid belt has these Kirkwood gaps in it, places where it's very difficult to orbit because you would orbit exactly twice for every one Jupiter orbit, or 3 times for every one Jupiter orbit. And so if a piece of an asteroid finds itself at that distance, it's very likely to be perturbed by Jupiter, get on an eccentric orbit into an Earth-crossing orbit, and then be collected as a meteorite. So obviously not a lot of asteroids are right there, but they're not too far away from it in semi-major axis. And so a chunk of an asteroid can come off, and then that Yarkovsky effect can cause its semi-major axis to drift, and then it enters the resonance and gets to Earth. So it's really possible that you have a very large asteroid, or you have one that's closer to Earth in many ways, but if it doesn't have access to one of these resonances that would put pieces of it on a Earth-crossing orbit, we might not sample that asteroid.
Next question. Are there any competing hypotheses against the streaming instability?
I didn't catch it all. Is our competing hypothesis against what?
The streaming instability.
Streaming instability? It's a relatively new model. In some ways, as the newcomer, the alternative hypotheses have been the ones that have been around for decades. This idea of hierarchical accretion, where you have meter-sized things bang into each other, from 10-meter-sized things and 100-meter-sized things and so on, that's the alternative. And it has a lot of flaws in it. One of the major ones is that this drifting process gets more efficient as you get larger sizes, and things that are meter-sized should drift through the disk in not just a few 100,000 years, but in a few thousand years. And we just can't keep them in the disk long enough. And so, I don't know. I mean, models have been developed, but they're not completely successful. And so I'd say the streaming instability is already, in just 10 short years since it came out, is almost a really, really good match to the data, in the sense that it predicts a power law distribution of asteroid sizes in the range that we expect, with something close to the power law, the exponent that we need. It provides a way to explain why chondrules are the things that comprise most of the asteroids, and it's astrophysically expected to occur, and so on. So I think that we'll have, kind of polished off all the loose ends by in the next 10 years. It's looking really successful.
Oh, thank you.
Have you tried overlaying this plot with the organic formation in the solar system? I know a lot of organics are incorporated from interstellar media, but a lot of them are also formed in the early solar system in the protostellar disk. And that is one of the problems with the aggregation model, the previous aggregation model, is that organics shouldn't form that close in.
No, I haven't, and now I'm interested to learn more about that. What we know we need to do next is we have a model that was geared to understanding the distribution of CAIs and refractory elements, And what we need to do now is figure out the distribution of water. I've shown here where you can have water, but we haven't predicted how much water you should have. I want to apply this to iron meteorites. There's a list of things that I have in mind to apply. I hadn't thought about the organic distribution. I thought about it a little bit when we were putting the paper together, because in the same way that there's a line inside of which water can't exist as ice, there is a line inside of which organics should combust and turn into CO gas. And I remember plotting that at one point, and it's sort of interior to here. It's sort of like right around where enstatite chondrites are forming. If you think that 400 Kelvin is enough to do that.
Oh yeah, 400 Kelvin will do it.
Yeah. So yeah, there's some line around here inside of which you couldn't retain primordial organics, but how the distribution goes, what I would predict, I don't know.
Yeah, because your time plot also tracks really nicely with so I study amino acids specifically, but the more the CM and CR tend to have the highest amount of amino acids, and CKs have almost none.
Mm-hmm.
That's also interesting.
Yeah, and in part that's because CKs, the parent body itself, reached some of the highest temperatures.
Yeah.
So it was very thermally metamorphosed. CV's less so. COCM's not much at all. So it might be a parent body effect as well.
One of the things that bothers the hell out of me is the mineralogy of CMs, in particular the abundance of kronstatite, which is one of these things that you just don't get hardly ever at all on the surface of the Earth. And the chemistry of that particular zone of the nebula just gives me headaches.
Right. I mean, that would be a parent body alteration effect, and I'm not really sure what gives you kronstatite versus some of the other ones. I mean,
well, it's the iron-rich end member of serpentine, and so you have to stuff Fe3 plus and Fe2 plus into the same crystal structure, and so you have to have an oxidation state or an oxygen fugacity that produces two different valent states of iron, which when you try to find kronstatite on Earth, you get it in tiny amounts in massive sulfide deposits that are quite often associated with really weird incompatible elements like pitch blende or uranium ores.
mm-hmm.
And so looking for kronstatites, you run into lots of unsavory people.
Oh, I see. Right, kronstatite is much more abundant in meteorites. I'm trying to remember the others, like saponite.
Yeah. Yeah, so you get odd chemistries in some of these things. Most of them seem pretty straightforward, but CMs are particularly weird, but CMs are also particularly attractive for resource potential.
I see. Okay.
Anyway, I think we're getting close to the end here. So if there's any more questions along the table or in the chat box.
I have one last quick question. So you said that as you move to the outer solar system, you get smaller chondrules?
Yeah, there is that tendency. It depends on this combination, surface densities, turbulence, which is varying in the nebula, et cetera. But this is what we predicted. And CI chondrites are forming in a region where the surface densities are low. That's basically it. The higher the density, that's primarily controlling it, the smaller the particle.
So
the smaller the density, the smaller the particle.
is there some theoretical maximum distance that you could form a chondrite then?
It would follow.
Not sure. Not really. you know, you would go to smaller sizes as you go further out. I think you're mostly running out of time to build something.
Excellent. Thank you.
So Steve, one thing I would ask you is if you could send me your slides or a PDF of your slides that I can put on the course website. And also these papers that you're referring to in your models, because I think that would be a valuable resource.
Sure. So the paper that I've referred to, that's published. It's a 2018 AppJ supplement paper. So all the references, the tables, et cetera, are in there. And I'll send you a PDF of the slides.
All right, appreciate it. And thank you very much.
All right.